Picture yourself driving uphill in a manual transmission car, stuck in first gear. The engine screams, the tachometer redlines, but you are barely crawling forward. Power exists, plenty of it, but you cannot access it where you need it. Now imagine that same problem, except you are 7 miles above Earth, chasing enemy fighters at 400 miles per hour, and your engine is gasping for air it cannot find. That was the reality facing every piston and engine fighter in the late 1930s. As aircraft climbed, atmospheric pressure dropped by half, oxygen mass flow collapsed, and horsepower evaporated precisely when speed and altitude meant survival. The solution? Make the engine breathe deeper as air thinned, continuously, automatically, without the pilot ever touching a control. It required rethinking the entire powertrain, from compressor blades to propeller pitch. The result was AIR superiority. Between 1935 and 1938, RAF planners faced physics they could not negotiate with. At sea level, a Rolls-Royce Merlin engine gulped dense air and produced over 1,000 horsepower. At 15,000 feet, that same engine wheezed out barely 600. Why? AIR density. For every 1,000 feet of altitude, atmospheric pressure dropped roughly 1 inch of mercury. Less pressure meant fewer oxygen molecules per cubic foot. Combustion requires mass, specific numbers of oxygen atoms colliding with fuel vapor, not volume. Thin air fills cylinders with emptiness. Engine designers knew this. Test engineers measured it on dynamometers in Derby and documented the brutal curves. Power versus altitude traced a diagonal line of defeat. The Spitfire prototype flew beautifully at 10,000 feet and felt sluggish at 20,000 feet. Intercepting high-altitude bombers demanded sustained power where natural breathing failed. The ceiling problem was not theoretical. It defined which fighters lived and which fell. By 1936, engine manufacturers had one answer: superchargers. Mechanically driven centrifugal compressors bolted to the engine, spinning at tens of thousands of revolutions per minute, ramming air into the intake manifold under pressure. Think of it as forced breathing, using engine power to pre-compress atmospheric air before combustion. Single-stage superchargers worked after a fashion. They maintained manifold pressure up to a critical altitude, typically around 16,000 feet for early Merlins. But here's the problem with that approach. The supercharger ratio was fixed. The impeller spun at a constant multiple of crankshaft speed, typically 6 to 10 times faster. At sea level, this overcompressed the intake charge, wasting power to drive the compressor and risking detonation. At high altitude, it undercompressed, leaving power on the table. Engineers calibrated for a compromised altitude, accepting inefficiency everywhere else. Test cells at Rolls-Royce revealed the thermodynamic trap. Compress air and it heats up. Hot air is less dense than cool air at the same pressure, which means fewer oxygen molecules again. Overboosting at low altitude did not just waste crankshaft power, it created scorching intake temperatures that triggered pre-ignition, where fuel detonated before the spark plug fired. Pistons hammered against rising pressure waves, connecting rods bent, engine life collapsed. The numbers told the story. A Merlin with a fixed ratio supercharger might produce 1,030 horsepower at its rated altitude of 16,250 feet. Below that height, manifold pressure had to be throttled back to prevent detonation, so power was limited artificially. Above that height, the supercharger could not maintain pressure, and power fell off a cliff. The efficiency band was narrow, perhaps 3,000 feet wide. Combat happened across 30,000 feet of sky. Why did more boost sometimes make power worse? Because compression ratio, temperature rise, and knock suppression formed an iron triangle. Push one boundary and another collapsed. The supercharger was a single gear in a race that demanded constant shifting. Meanwhile, in 1937, propeller specialists confronted a different mismatch. Piston engines produce maximum power at specific revolutions per minute, typically 2,400 to 3,000 for the Merlin. Propellers, however, need different rotational speeds depending on flight conditions. During takeoff, a coarse pitch, a shallow blade angle, at high revolutions per minute absorbs engine power efficiently. In cruise, a fine pitch at lower revolutions per minute provides thrust without overspeeding the blades. Fixed pitch propellers forced a compromise. Set the blade angle for climb performance and you over-rev the engine on takeoff, hitting red line limits before the aircraft even leaves the ground. Set it for cruise efficiency and the engine lugs during climb, like a car struggling uphill in top gear. Pilots lived with the wrong propeller setting for every flight condition except one narrow design point. Two position propellers helped slightly. The pilot could manually select coarse or fine pitch via a cockpit lever, mechanically adjusting the blade angle through an oil pressure system. Better than nothing, but now the pilot was managing throttle, mixture, revolutions per minute, boost pressure, and propeller pitch simultaneously while dogfighting. That caused cognitive overload in a high G environment where seconds mattered. Think about the mechanics. Engine torque arrives in pulses. Each piston fires and drives the crankshaft in intermittent surges. The propeller resists with aerodynamic loading that varies with blade angle, airspeed, and air density. Mismatch those forces and you get torsional, vibration, efficiency loss, or structural damage. The engine wants to run at its power peak. The propeller wants rotational speed matched to thrust requirements. They disagreed constantly. Test pilots reported the consequences. In combat climbs, the engine would scream at maximum revolutions per minute, while the propeller, set too coarse, failed to absorb the available power. Or the opposite, fine pitch during high-speed dives would windmill the propeller and overspeed the engine dangerously. Either way, the pilot fought his own machine. What if the engine and propeller could synchronize automatically? What if blade pitch adjusted continuously, governed by a mechanical feedback loop that held engine RPM constant, regardless of throttle position or flight conditions? That would free the pilot to focus on flying and let the power plant operate in its ideal regime at all times. The technology existed, constant speed governors originally developed for industrial machinery, but adapting them to aircraft propellers demanded solving problems of weight, reliability, and oil pressure control at altitude. The system bottleneck was becoming clear. You needed active, automatic matching of engine breathing and propeller loading continuously. In 1938, at Rolls-Royce's Derby facility, Stanley Hooker confronted the supercharger's fundamental limitation. A brilliant mathematician turned engine designer, Hooker had studied compressor aerodynamics at Oxford before joining Rolls-Royce. He understood that the single-speed supercharger was a brute force tool in a situation demanding finesse. His solution was two-speed supercharging. Instead of one fixed gear ratio, the system used two, a low ratio impeller for lower altitudes and a high ratio for upper altitudes. The pilot would manually shift between them at a predetermined height, typically around 19,000 feet for the Merlin 45. Below that altitude, low gear provided adequate boost without excessive power consumption. Above it, high gear maintained manifold pressure as atmospheric density plummeted. Think of it like a transmission. The engine's crankshaft drives the supercharger through a gear train. In low gear, the impeller might spin at 6.4 times crankshaft speed. In high gear, that ratio jumped to 8.15 times. The shift happened by a hydraulic clutch mechanism where oil pressure engaged different gear sets without stopping the engine. Sudden? Potentially. The trick was timing the shift to avoid shocking the intake system with a pressure surge. The engineering required precision. The impeller itself, a centrifugal wheel with curved vanes, had to tolerate rotational speeds exceeding 25,000 revolutions per minute while pumping hundreds of pounds of air per minute. Aerodynamic loading created enormous centrifugal forces. The aluminum alloy blades needed strength without weight, balance without vibration. Diffuser vanes downstream of the impeller slowed the high-velocity air, converting kinetic energy into a pressure rise. Get the diffuser geometry wrong, and airflow separated, stalled, or surged backward. Two-speed supercharging brought altitude performance, but it was not perfect. The shift point was abrupt, and manifold pressure jumped as the higher gear engaged. Pilots had to anticipate the transition, pulling back the throttle momentarily to prevent overboost. Still, Merlin 45, introduced in 1940, demonstrated the concept's power. Full throttle height in low gear was 11,000 feet at 1,300 horsepower. Shift into high gear, and the engine maintained that power to nearly 20,000 feet. How do you shift boost without shocking the engine? Through hydraulic clutches, precisely timed pilot input, and careful calibration of pressure relief valves. The mechanism worked because it matched the compressor's capability to the atmosphere's density. The engine did not know it was climbing. Manifold pressure stayed constant, combustion remained optimal, and power delivery smoothed out across a vastly expanded altitude range. The next step would be even more ambitious: two-stage supercharging, where one compressor fed another in series. By 1939, compressor designers were pushing deeper into fluid dynamics. Inside a supercharger, air does not simply get squeezed, it gets accelerated, diffused, and thermodynamically transformed. Understanding this process required thinking about blade geometry at a micro level. Picture the impeller as a centrifugal pump for gas. Air enters at the hub, near the center, moving slowly. The spinning vanes catch it and fling it outward through curved passages. As air accelerates radially, velocity increases dramatically from perhaps 200 feet per second at the inlet to over 1,500 feet per second at the impeller tip. Kinetic energy skyrockets, but engines need pressure, not velocity. That is where the diffuser comes in. Immediately downstream of the impeller, a ring of stationary vanes forces the high-speed air to slow down. As velocity drops, pressure rises. Bernoulli's principle in action. Think of it like a river widening. The same mass flow spreads out, current slows, and depth increases. Properly designed, a diffuser converts 70 to 80% of velocity energy into pressure. Why did blade shape matter more than size? Because of how air behaves at high speeds. Make the impeller vanes too straight, and airflow separates from the surface, creating turbulence and efficiency loss. Make them too curved, and you induce secondary flows that waste energy. The optimal profile is a subtle curve, enough to guide the air smoothly, but not so aggressive that it stalls the boundary layer. Metallurgists struggled with material science. Aluminum alloys strong enough to withstand centrifugal stress tended to be brittle. Ductile alloys could not handle the revolutions per minute. Rolls-Royce developed proprietary aluminum alloys with magnesium and copper additions, achieving tensile strengths over 30 tons per square inch while maintaining workability. Each impeller was dynamically balanced to tolerances of a few thousandths of an inch, critical at 25,000 revolutions per minute, where even tiny imbalances generated destructive vibration. Then came two-stage supercharging. Instead of one compressor, engineers used two compressors in series. The first stage provides moderate boost, perhaps raising manifold pressure from 10 pounds per square inch to 20 pounds per square inch. The second stage takes that pre-compressed air and boosts it again, reaching 30 pounds per square inch or more. The pressure ratio of each stage is manageable, avoiding surge and excessive temperature rise, but the combined effect is multiplicative. The Merlin 60 series, introduced in 1942, featured two-stage, two-speed supercharging. Low-low gear for sea level, low-high gear for mid-altitude, high-low and high-high gears for extreme heights. 4 effective ratios, each optimized for a specific flight regime. Critical altitude exceeded 30,000 feet. That was double the original Merlin ceiling. That's when blade shape, not just engine displacement, became the defining factor in air superiority. Meanwhile, in 1940, control engineers were perfecting constant speed propellers. The concept was elegant: use engine oil pressure to automatically adjust blade pitch, governed by a mechanical feedback loop that maintained constant RPM. Here's how it works. The propeller hub contains a hydraulic piston connected to the blade roots. Oil pressure supplied from the engine's lubrication system pushes the piston forward, increasing blade pitch, so the blades bite more air and become coarser. A spring or counterweight mechanism pulls the piston back, decreasing blade pitch so the blades become finer. The governor, a small centrifugal flyweight mechanism, sits on the propeller shaft and senses rotational speed. If engine RPM rises above the pilot's selected setting, the flyweights spin faster and move outward against spring tension. This movement opens an oil port and directs high-pressure oil into the propeller hub. Blade pitch increases. The propeller absorbs more power, and engine RPM drops back to the target. If RPM falls below the setting, the flyweight's slow, the spring closes the oil port, pitch decreases, and RPM rises. The cycle repeats continuously, hundreds of times per second, maintaining speed within a few RPM of the desired value. Think of it as an automatic transmission, but for rotational speed instead of vehicle velocity. The pilot sets a target RPM using a cockpit control, typically 2,650 RPM for maximum power or 2,400 RPM for cruise. The governor handles everything else. Full throttle for takeoff, the propeller coarsens automatically to prevent overspeeding, throttle back for descent, and it fine-tunes for efficiency. The pilot does not touch the propeller control again until changing power settings. The mechanical ingenuity is beautiful. No electronics, no computers, just calibrated springs, centrifugal forces, and hydraulic pressure. Oil pressure becomes the control medium because it is already available on every aircraft engine. It is incompressible, which provides precise actuation, and it works at altitude, unlike pneumatic systems that depend on air density. Tolerances mattered enormously. The governor's flyweight assembly had to be balanced to micrograms. Oil ports needed lapped surfaces with clearances measured in 10,000ths of an inch to prevent leakage. The blade pitch mechanism required rotary seals that would not leak under centrifugal force while spinning at 2,000 plus RPM. How does oil pressure become an automatic transmission? Through negative feedback loops. The system constantly measures its own output, RPM, compares it to the desired set point, and adjusts inputs, blade pitch, to eliminate error. This principle of automatic control via feedback was revolutionary in 1940 aviation, though it had existed in industrial governors since the 1700s. The propeller now matched engine behavior dynamically, but the real breakthrough came when constant speed propellers were integrated with variable supercharging. By late 1940, airframe integrators understood they were not optimizing components, they were orchestrating a system. Engine, supercharger, and propeller had to work in harmony. Their torque, curves, and power absorption characteristics aligned across the entire flight envelope. Think about what happens during a combat climb. The pilot advances the throttle to maximum power and sets propeller RPM to 2,650. As the aircraft accelerates and climbs, air density drops, but the two-speed supercharger maintains manifold pressure. The engine produces consistent torque. Meanwhile, the constant speed propeller continuously adjusts pitch to absorb that torque while holding RPM steady. The pilot flies, and the power plant manages itself. Without this integration, the pilot would be chasing gauges, adjust the throttle, and then RPM climbs too high. Reduce propeller pitch and manifold pressure spikes. Pull back the throttle and you lose airspeed. The human reaction time, perhaps 0.5 seconds per adjustment, could not keep pace with the aircraft's dynamic changes, especially in combat maneuvering where G-forces, altitude, and airspeed shifted constantly. Test pilots reported the transformation. Captain Eric Brown, who flew nearly every World War II fighter, described the Spitfire Mark IX with a two-stage Merlin and a constant speed propeller as harmonious. Throttle response was immediate and predictable. Climb performance was smooth, not lurching through supercharger shift points. Engine temperatures stayed within limits because the system prevented overboost and detonation. The engineering behind this harmony involved matching torque curves to propeller absorption. The Merlin's torque peaked at specific RPM. The constant speed governor held the engine in that power band. The supercharger ensured adequate air mass regardless of altitude. The propeller, adjusting pitch continuously, absorbed available power without overspeeding or lugging. Every component operated in its optimal regime simultaneously. This was systems thinking before the term existed. Not bigger engines or more powerful compressors, but intelligent coordination. A 1,300 horsepower Merlin with integrated systems could outperform a 1,500 horsepower engine without them, because useful power actually transmitted to thrust, depends on the entire drivetrain's efficiency. Why did systems thinking beat raw horsepower? Because aircraft performance is not determined by peak power, but by sustained power across mission profiles. A fighter that maintains 1,200 horsepower from sea level to 25,000 feet will outclimb, outrun, and outlast one that makes 1,400 horsepower at its optimal altitude but falls off everywhere else. Integration converted potential into performance. In 1940, frontline squadrons encountered the practical consequences. RAF Fighter Command began receiving Spitfire Mark IIs with constant speed propellers in June, followed by Mark Vs with improved Merlin 45 engines later that year. Pilots noticed immediately. Scramble orders demanded rapid climbs to intercept altitude, often 20,000 feet or higher, to meet incoming bomber formations. With fixed-pitch propellers, the climb was a compromise, either over-revving the engine at low altitude or lugging it higher up. Constant speed propellers eliminated the choice. Full throttle, 2,650 RPM, and the system optimized automatically. Climb rates improved 10 to 15% across the board, but sustained power above 20,000 feet was the real revelation. Earlier Spitfires felt breathless at altitude, power dropping noticeably above 18,000 feet. The Mark V, with its two-speed supercharger, maintained rated power to 19,000 feet in low gear, then shifted to high gear and held it to 29,000 feet. Combat that had been sluggish at extreme altitude became energetic. Turn rates stayed high. Acceleration remained crisp. Maintenance chiefs tracked reliability. Constant speed propellers required periodic governor overhauls and oil seal replacements, but failures were rare. The mechanisms proved robust under combat stress, high G maneuvers, rapid throttle changes, and emergency dives. Two-speed superchargers needed clutch inspections, but the system tolerated hard use. Tolerances held. Components did not fail catastrophically. What changed when fights moved vertical? Altitude performance became dominance. German Bf 109Fs with fixed-pitch propellers and single-stage superchargers could compete at medium altitudes but lost effectiveness above 22,000 feet. Spitfire pilots learned to climb above enemy formations using superior high-altitude power to dictate engagement terms. The numbers validated the technology. A Spitfire Mark V climbed to 20,000 feet in 7.5 minutes, nearly 2 minutes faster than a Mark I. Service ceiling increased from 34,000 feet to 37,000 feet. At 25,000 feet, maximum speed jumped from 355 miles per hour to 374 miles per hour. These were not marginal gains. They were operational advantages that shifted air superiority. Pilots stopped thinking about engine management and focused on tactics. The constant speed propeller became invisible, proof of perfect engineering. When a system works so reliably, you forget it exists. The designer succeeded. The cockpit workload dropped and situational awareness improved. That cognitive margin, freeing pilots from mechanical management, saved lives. Between 1940 and 1941, Britain faced industrial reality. Brilliant engineering means nothing without mass production. Rolls-Royce and Rotor, a propeller manufacturer jointly owned by Rolls-Royce and Bristol, had to scale constant speed governors and two-stage superchargers from experimental units to thousands per month. The challenge was precision at volume. Governor flyweights required dynamic balancing to tolerances of 1,000th of an inch, achievable in a laboratory but difficult on a production line. Oil seals for propeller hubs needed lapped surfaces that would not leak under centrifugal stress. Supercharger impellers demanded consistent blade profiles because a warped vane could cause vibration that would destroy an engine. Factory managers implemented quality control protocols borrowed from watchmaking. Each governor assembly was test run on calibration rigs, adjusting spring tensions until RPM stability met specification. Impellers were x-rayed for internal voids in the aluminum casting. Propeller blade pitch mechanisms underwent pressure testing while submerged in hydraulic fluid, cycling through the full travel range. The numbers were staggering. By mid-1941, Rolls-Royce was producing over 1,000 Merlin engines per month. Rotor delivered constant speed propellers at matching rates. Reject rates for governors hovered around 8%, high by modern standards, but acceptable given the complexity and wartime urgency. Engines that failed acceptance testing were disassembled, faulty components identified, and production processes adjusted. How did tight tolerances become a weapon? Because reliability multiplied effectiveness. An unreliable, constant speed governor meant pilots reverted to manual pitch control, negating the system's advantages. A supercharger that surged or seized grounded aircraft. The Royal Air Force needed not just advanced technology, but dependable advanced technology delivered in quantity. British industry met that standard by treating precision manufacturing as seriously as design innovation. Tolerances were not perfectionism, they were operational requirements. By 1941, Allied analysts were comparing performance across air forces. The data revealed why the Merlin's integrated systems conferred such decisive advantages. Consider the power to altitude curves. A German DB601 engine in the Bf-109F produced 1,350 horsepower at its rated altitude of 16,400 feet with a single-stage, single-speed supercharger. Below that height, manifold pressure had to be throttled back. Above it, power fell steeply, down to 950 horsepower by 25,000 feet. The Merlin 45, with two-speed supercharging, made 1,515 horsepower at 11,000 feet in low gear and maintained 1,230 horsepower at 19,000 feet after shifting to high gear. More importantly, power remained above 1,000 horsepower all the way to 29,000 feet. The performance envelope was vastly broader, less peak power at one altitude, but far more usable power everywhere else. American pilots flying P-51 Mustangs with Packard-built Merlins, produced under license in the United States, reported similar dominance. The Mustang's two-stage two-speed Merlin 60 series engine delivered over 1,500 horsepower at 25,000 feet, enabling bomber escort missions deep into Germany where earlier fighters could not operate effectively. Why could not rivals copy it quickly? Several reasons. First, the metallurgy for two-stage impellers was proprietary. Rolls-Royce aluminum alloys were not available to Axis manufacturers. Second, the control systems, constant speed governors, and hydraulic clutches required precision manufacturing infrastructure that took years to develop. Germany had excellent engine designers, but faced material shortages and dispersed production that hindered quality control. Third, system integration required cross-disciplinary expertise. Supercharger aerodynamicists had to coordinate with propeller control engineers, who coordinated with engine calibration specialists. This holistic approach, common in British aerospace development, was less established elsewhere. German manufacturers optimized components individually, and integration happened late, if at all. The proof appeared in combat reports. Spitfire Mark V aircraft intercepted Bf-109Fs at altitudes where the German fighters struggled. P-51D Mustangs escorted bomber formations to Berlin and back, outrunning Luftwaffe interceptors. Power delivery across the flight envelope, not just peak horsepower, determined air superiority. The Merlin's integrated systems delivered that envelope. Rivals recognized the gap but could not close it before the war's end. Between 1942 and 1944, Merlin refinement continued with intercooling. Two-stage compression generated heat. Cooling the air between stages increased density, allowing higher boost without detonation. Radiators placed in the airframe airflow chilled the compressed charge before it entered the engine. Power climbed past 2,000 horsepower in late war variants. Metallurgy improved with stronger alloys and better coatings. Reliability increased even as boost pressures soared. How did cooling unlock more power safely? By managing the thermodynamic limits that had constrained earlier engines, turning physical constraints into engineering opportunities. Post-war, constant speed propellers became aviation's default. Airlines adopted them for every piston-powered transport. Cessnas and Pipers installed them on small aircraft. Certification bodies made them standard equipment. The technology Rolls-Royce and Rotal perfected under wartime pressure became civilian infrastructure. Pilots worldwide benefited from reduced workload and increased efficiency. Why did pilots stop chasing RPM? Because automatic systems, once proven reliable, became invisible. Engineering absorbed into expectation. Today, the lineage persists. Turboprop aircraft use constant speed propellers governed electronically. Variable geometry turbines adjust compression ratios automatically. Every modern engine, whether jet, turboprop, or automotive, employs automatic control loops descended from the 1940s supercharger governors. The principle survives: match power delivery to demand continuously. Modern engineers learn these systems without knowing their origin. Where do you see this gear changing idea now? Everywhere, invisibly, perfectly.